Hello everyone, in this video I'd like to talk about the DDNM method that uses diffusion models as a zero-shot image restoration task. And that means it can be used for very cool applications like super resolution or inpainting or colorization or a mixture of all of it for image restoration. But the cool thing about it is that it doesn't require any training at all, and it does it in a zero-shot manner. I hope you enjoy it, and let's just see how it works. In image restoration problems, we have an input image X, our high quality image, that you can imagine it as a giant vector, and there is a linear degradation operator A that is multiplied by this image, and we have Y, our observation. What is given to us in reality is this vector Y, which you can imagine it as a degraded image, such as a grayscale image or a low resolution image, and our goal is to recover X given this observation. Well, you might say if we have this matrix A, then we can multiply this equation by the inverse of this matrix and we can easily solve it. But the thing is that this matrix is not necessarily invertible, and also we have additional unknown noise that is added in real life that we don't have access to it, and that makes the task more challenging. In traditional image restoration methods, people tried finding a solution by optimizing this formula. That our goal is, among all the possible X values, we want to find the one that if we multiply it by A, the difference between the degraded image and the observation is minimized as much as possible, and also a regularization term that should work as an image prior. Because you can imagine an easy way for solving, let's just say, a super resolution task is just to upsample the given Y vector using nearest neighbor upsampling, and we have a higher resolution image X that if you multiply it by matrix A again, the difference between AX and the observation is 0. But that high resolution image X is pixelated and it doesn't look like real to us. So we have this second term as a regularization just to make it more real. And we'll see visual examples later in the video, but in a nutshell, we have the second term to mitigate the issue. And people have tried things such as ridge regression, also known as Tikhonov regularization as the image prior term. And finally, we have our estimated high quality image X hat. Seems straightforward, I hope, but the issue is that it is not realistic when we solve this problem using this formula, and the solution is far away from the actual X vector we have in the real life. So people have tried using deep neural networks that is actually easier to understand. We have a bunch of high quality images X and corresponding degraded image Y, and we train a neural network by optimizing its parameters theta, that if the neural net receives the degraded image Y as the input, it has to give us the high resolution image X as the output, and we penalize it if it can't. And we optimize it using all the training data that we have, and we find a better estimator compared to the previous classic method. So now what's the issue? Well, first of all, it's a neural net, so it's not interpretable how it turns a lower quality image to a higher quality image. But what is more important, I guess, is that it is sensitive to domain shift, meaning that let's just say the Y images are blurry images that the neural net has to deblur them. And if the training data are generated using a Gaussian filter with some kernel sizes, it wouldn't work as inference time if we use a Gaussian blur with a different kernel size, because it hasn't seen it in the training data. Another more recent approach is using generative models in zero-shot manner. To do that, at inference time, we solve this optimization per each given image, and we find the best W latent vector that if we give it to our generator, it should generate a high quality image that if we degrade it by multiplying by matrix A, it should have the least mean squared error with the observation Y. And also we follow an image prior that we can define. But note that similar to classic methods, when the optimization is made of sum of two terms, we have two different aspects to consider. First term is called data consistency, meaning that whatever high quality image I make, the only thing that matters to me is that if I degrade it, it should have the same structure as a lower quality image. Like for the case of image colorization, you can think of any combination of colors that you can assign to different objects, and you don't care about the appearance as long as you can get the same gray image when you apply the degraded image and have a grayscale image, for example. But the second term is realness, and that means it should follow the image priors. And in our example, it means that you cannot assign a red color for grass as an example, and it has to be green. Don't think about how you can assign a good image prior for now. What you have to know is that when using generative models, it is often hard to balance realness and data consistency. And to visually show what I mean, let's imagine we have this observed image Y, and our job is to reconstruct the high resolution image of it as a super resolution task. One reconstruction X that we can have is this thing that is as simple as nearest neighbor upsampling. The thing you can see with this reconstruction is that the data consistency is perfect. If I downsample the image by multiplying it by the degradation matrix A, I get the exact same observation Y that I have. But the realness is an issue since the image is pixelated and doesn't follow the natural image prior, that there has to be a smooth transition between the colors, and there are some intricate details about this image. And another reconstruction X that we can have is this image, that the realness is perfect. As you can see, it is a high resolution image, but the data consistency is an issue because if I downsample the image, then the low resolution image I achieve is not the same as observation Y anymore, and there's a difference between the two. So what I want is a perfect balance between the two to satisfy both conditions, and if I can do it, I will achieve this high resolutional image. And that's where the paper comes in to propose Range-Null-Space decomposition, and leverages the same basic concepts in linear algebra that hopefully we all know, that are range space and null space, and uses that to maintain the balance. But if you don't remember much, don't worry about it, because now I want to explain it visually what it means. Let's assume we are in a three-dimensional space and have two vectors that are linearly independent. When I say they are linearly independent, I mean that you cannot write one by simply multiplying the other one by a singular scalar value. And as you know, two linear independent vectors should create a plane that is a subspace if we consider these two red vectors as the bases. Coming back to our problem, we have this y equals ax. The matrix A is a small d times capital D dimension that turns the vector x into vector y. In the example I show you in the right, it should turn a three-dimensional vector x to a two-dimensional vector y that I will show you in a second. Obviously, this matrix is not invertible, and because it's not even a squared matrix. But the thing is, we can compute the pseudo-inverse matrix A dagger, that what we expect from it is that if we multiply A dagger by A, and then multiply it by A again, we expect the value of the final result to be estimately equal to the original matrix A. And that means A dagger times A should try its best to create an identity matrix. And now here comes the interesting idea that if x is a capital D dimensional vector, in our example three-dimensional vector, then A dagger A samples to range space of A. But what does it mean? Let's say I have this arbitrary x vector in three-dimensional space. When I multiply by A, all the thing that A does is a projection that maps this three-dimensional vector x into AX, which can be represented as a 2D vector in that plane. Here in visualization, I'm showing it as orthogonal projection, and that requires an assumption that these two red vectors are unit vectors, but it's not really important for what I'm about to say now, so don't focus on that much. But the thing that we care is that when we solve this y equals ax, all the y vectors that the matrix A can output are all the points within this plane, and all the points within this plane are called the range space of matrix A. So when we say about the range space of A, this 3D blue vector is not in the range space of A because it's outside of the plane, but this 3D blue vector is in the range space of A because it is inside the plane, and I can also represent it as a 2D vector that's a linear combination of two red vectors. So hopefully the notion of range space makes sense now, but what does it mean that A dagger A samples to range space of A? Well, we all know that x is a vector, right? If I multiply it by A dagger A, it is still a vector, and if I multiply it by A matrix again, it is still a vector. But remember from above that A dagger A is estimately equal to BA? Well, guess what? I have it right here. So I can say A dagger AX is estimately equal to AX, and what is AX? It is Y. And now what I hope you to say is, okay, Suruj, you said something that mathematically it makes sense, but I cannot really understand what's the point of all of this, and I'm a bit confused. If we are on that point, that's a good news, because now I want to clarify it. When we say a dagger A samples the range space of A, it means that out of all the possible 3D vectors X, it selects a subset of vectors that let's denote them by a dagger AX, that these vectors should be all the vectors that we need, that if we multiply all of them by matrix A, we can construct every possible vectors in that red plane. And to visually show you what I mean, assume that we have this AX point in the plane. The A dagger AX should be hopefully the same X that we have. But now let's just say I have another vector Z in the 3D space. And here comes the interesting thing, that if I multiply it by A dagger, it doesn't go back to Z and instead go back to X. And that's what I mean by that subset. You can see that clearly vector X is within that subset of A dagger AX, but this vector Z is not within that subset. And the whole point of this decomposition is to decompose the vector X and Z. You can imagine vector Z and all the other vectors that they are in the dotted line as variations in the 3D that has no effect on the projection AX. So if I decompose these two notions and move only in the direction of dotted line, I can tune the realness without worrying everything about the data consistency, because no matter how I change it, after projection to 2D space, there is no difference. And to represent all these variations in the dotted line, you can solve this equation that gives you the vectors in the form of I minus A dagger A multiplied by X. That is all the vectors in the dotted line, and if you're interested to know how this is achieved, in linear algebra we define all the vectors in null space of A, that we can achieve them by solving Ax equals 0. That you can achieve the same thing with this equation, because when you multiply A and X to elements within the parentheses, you will reach Ax minus Ax. That means no matter what I pick for X, it becomes 0 and it is in the null space of A. So hopefully the intuition makes sense. And now what we need to do is to write a decomposition of X in the form of these two terms. That the first term is vectors in the range space of A, and the second term is null space of A. And you can multiply X to elements inside the parentheses just to see that this equality holds. And as I mentioned before, if I keep the range space constant, I can be pretty sure that after projection to lower dimensional space, I have the data consistency constraint fixed. And all I need to do is just adjust the null space to change variation in a higher dimensional space and make it more real. And others in this paper said, let's just use diffusion models to refine the null space. So null space is all we need, right? To see what you have to do, let's come back to our problem y equals ax. We have ground truth image x, a high dimensional image, and we multiply it by degradation operator that has to make it have a worse quality, and we have y, our degraded image, as the output. After solving the IR task, we hope to estimate an X vector that satisfies two things. First is the data consistency, and the other is realness. We can consider realness by assuming that you have a distribution of images, let's just say Q of X, that we can sample from it, and it just outputs an actual image, kind of like a diffusion model or GAN, that we can generate realistic images. What we can say about the realness of an estimated vector x hat is that it should be very close to what is outputted by sampling from this distribution Qx. And remember this range space null space decomposition from the previous slide, we can denote it this way, that we can substitute ax by the observation y, and since we don't have access to the real high quality image x, we substitute it by x bar that we have to achieve. So our goal is to find a proper x bar that once you look at it, it looks like an image sample from the distribution Qx of real images, like the ones generated from a diffusion model, and now let's just see how we can do that. So we have to refine the null space iteratively. And recall in backward diffusion of diffusion that we want to reach xt-1 from xt by defining a normal distribution with a specific mean and a variance in a particular step. The mean is defined using this formula and the variance using this formula, that they both rely on alpha and beta hyperparameters unique per each time step. And the denoiser network has to estimate the noise epsilon to reduce it from xt to reach xt-1. But the issue is that if I want to use it for the image restoration task, This process is completely random, and there is no guarantee to reach the high-resolution image X that preserves the data consistency term. So to solve this issue, the authors say, let's just use this method similar to DDIM, that we keep the variance same as what it used to be, but change the mean to be a linear combination of x0 and xt. Kinda same as DDIM, that we first estimated xt and added noise with a less severity to reach xt-1, if you remember from the video I posted. And like the DDIM, we don't have access to x0 and we have to estimate it. And for estimation, we just use the single step diffusion, so the denoiser z theta has to estimate the noise and we subtract from xt with a joiner step to reach x0. But now we still have an issue. And what's the issue? The issue is that the estimated x0 does not satisfy the data consistency term, that if we downgrade it using the matrix A, we have to achieve the low resolution image Y. And to solve this issue, we can rely on the decomposition of range space and null space that I just told you, and keep the range space intact, and only modification is just to modify the null space by replacing the x bar that I told you with the output of this diffusion. So using this, we reach a new x0 hat that the range space constraint is satisfied, and if I degrade it, I should get the same observation Y, but the null space at each time step is refined to make it a high resolution image more real. And so we use the new x0 hat in the update formula of DDIM to go from xt to xt-1. But note that there is one element of random noise that we also have to add as an element of stochasticity to have the diversity in our image restoration task, and also help the model to find a path in the denoising step to erase the disharmony between the range space and null space. And to visually show you what happens, let's assume that we have ground truth high resolution image of a squirrel, but what is given to us is a low resolution image Y, and our task is a super resolution task. If we simply multiply the observation Y by a dagger, it acts as something like a nearest neighbor upsampling, that if you look at closely, you might notice that the quality of the fur is a bit different compared to the ground truth. And now let's see what happens in the denoising steps of the diffusion. Here we have each column representing a different denoising step starting from 900 and 5-step DDIM to reach the end. Focusing on the first column, we are at step 900 that xt is nothing but a pure noise. If we use our denoiser z theta to estimate x0 in a single step, we will reach this image that is similar to what I've shown you in the DDIM video for a Persian rug. But once we update the x0 by keeping the range space intact and refining the null space, we have this x0 hat that you can see that at the worst case scenario it should be equal to a dagger Y, such that when I multiply it by a, I get the same observation Y. And then in the future columns you see that it refines the null space and adds more details in the 4 area, so it becomes a higher quality one. And to visually summarize the denoising step we have to do, let's assume we started from the x capital T and now we are at xt. Our job is to denoise it in one step and reach xt-1. To do that, we first estimate the noise and come back to x0 using a single step denoising, then we decompose it into range space and null space. Range space comes from the observation Y, so the bad quality of the estimated x0 has no effect on it, and the null space is refined by our estimation, and we add them up to get x0 hat that we use in the denoising step to reach xt-1. And we iterative this procedure until we reach x0 at the end. So far, hopefully the general idea makes sense. Now you might wonder how we can reach matrix A and a dagger to use it in the denoising step. For constructing matrix A, we define a unique per image restoration task. For inpainting as an example, we have this constraint that if we multiply the matrix A 3 times, we should get the original matrix A. And in general, in linear algebra, we have a concept called idempotent matrix, that you can multiply it by itself no matter how many times and you still get the same matrix. But here is a special form of it, because what we care is 3 times multiplication, not more or less. But before explaining why we need that, to construct such a matrix, we have to define it as an involuntary matrix, that are groups of matrices in linear algebra that are equal to their inverse or pseudo-inverse of themselves. And if we define it that way, then multiply A by itself is like multiplying it by its pseudo-inverse that should make it identity matrix. And then multiplying it again by A should be equal to A, because A times identity matrix is A again, and it satisfies the condition. But why do we need to define it that way? Because for in-painting task, our job for degradation is nothing but masking some areas of the image. And so this matrix A should mask out some pixels while keep other pixels unchanged. And once I multiply it by itself, it should be equal to multiplying it by inverse of it. And multiply by inverse intuitively means to reconstruct all the missing pixels. And finally, multiplying it by A again means in-painting it again. And the right side says it should be equal as applying in-painting once. So when you think about it, it's an interesting way of saying that when I in-paint an image, paint it again using a neural network, and in-paint it again, it should be exactly the same as one time in-painting. And that constraint only happens when the neural network that has to paint is not allowed to paint the available pixels, and it has to only paint the missing values. And for colorization, we can define degradation as a matrix that all it does is averaging the RGB pixels to make a single channel image representing a grayscale image. And as you can guess, the pseudo-inverse should be this A dagger that all it does is that it repeats the same channel 3 times to represent the RGB image. Obviously, A dagger Y is not the same as X anymore, and that's why we have a diffusion model to refine the null space and make it more realistic. And for super resolution task, we can assume that we have a matrix A that receives patch of n times n pixels in an image and turns them into a single pixel similar to average pooling that we have in deep learning. And then we can define it this way that takes average of n squared pixels that we have in a patch and put it into a single pixel. And again, for A dagger, as you can imagine, we have this thing that repeats the pixel n squared times and upsamples the image. And what is cool about this method is that it is all linear algebra. So for complex tasks like old photo restoration, we can multiply in painting, colorization, and super resolution degradation and do all at the same time to degrade the image. And obviously, the pseudo-inverse would be the multiplication of all the defined pseudo-inverses in a reverse order. Sounds cool, right? But life is not that easy, and if you try this thing I told you so far, you see that it doesn't work very well in practice. And why is that? Well, they define something called DDNM plus for that. But back to the question that why it doesn't work, it's because in practice we have an element of noise as added and it's overlooked so far. For simplicity, we can assume this noise to be a random Gaussian noise with mean of 0 and some variance, that each dimension out of these dimensions are independent and have no influence on each other. Why is it problematic? Because recall this formula that we used for decomposition, that if you replace y vector in this formula by ax plus n, then we have an additional a dagger n in the formula that we overlooked in our calculations so far. That's a new vector in capital D dimensional space that kinda ruins it and makes a task harder than what we thought. But don't worry about it much, because even though we don't have access to it, the previous term that we subtract is an important term called correction of range space. It simply says inside the parentheses that once we have the estimated x0 vector, we can multiply it by a and compare it with ax, which is y, and it is our observation, and see how much error do we have in our estimation. Note that some of these errors could be because of the a dagger noise that is added and we don't have control over it. If we didn't have this element of noise, we could simply assume that all the errors we have inside the parentheses is nothing but our error in the estimation. So we multiply it by a dagger to turn it back into capital D dimensional space and subtract it by our estimated x0, and have our x0 hat that doesn't have any error in the estimation. But now that we have this element of noise, that means that some of the errors inside the parentheses is because of the actual noise that we have in the observation. So we shouldn't fully remove all the errors in the parentheses, because if we do, then that means we solve it by having the noise in our problem. And to mitigate this issue, we can define this formula that's exactly the same as what it used to be, but now for reducing the errors in range space, we multiply it by sigma t, d times d dimensional matrix that is covariance matrix, forcing to take the error into consider. But there are two things we should note now. First, the total variance xt-1 after denoising should confirm the definition of forward diffusion that we reach xt-1 given the x0. So we cannot just arbitrarily change the sigma t matrix and reach a variance that the denoiser doesn't expect. Because remember, at the end of the day, we have a zero-shot method that we don't tune the parameters. And if you don't tune the parameters of the diffusion, and at the inference time, the diffusion, it should see whatever it has seen during the training and not something unexpected with some unknown variance. And the next thing is that what we want is that the sigma t to be as close as possible to identity matrix to fully correct the range space. And now let's just see how we can get the metric sigma t. Recall that for most image restoration tasks, a dagger was nothing but replicating the numbers and is a copy operation. And since for simplicity we assume that the element of noise is coming from a random normal Gaussian, that each dimension is independent, we can assume the same thing for a dagger n, that each dimension is independent. And if independent, that means off-diagonal entries in covariance matrix should be 0, so nothing but an identity matrix multiplied by lambda t. So let's see how we can define this lambda t. Note that as I told you, the variance should confirm the definition of forward diffusion. Recall in denoising a step we had this formula. Let's look at the elements that affect the variance. First thing is this term that let's denote it by at and write it here. The second term is lambda t, of course, that we have to find the value. And to keep the total variance intact, the third thing is the sigma y, that's the standard deviation of the element of noise that we don't really have access to it. And since we don't know it, we can consider it as a hyperparameter just by looking at the picture and decide what to choose for this value. And I will show you later visually how it affects the final performance. We raise this multiplication to the power of 2 to make it variance, and then we say that it should equal to the sigma t squared, that the variance of the denoiser added in the denoising step of diffusion, that should also follow the variance that the model expects. But then it comes another idea that says we shouldn't add much of a noise in the denoising step if the element of noise we have in observation is much. So they defined phi t, which is again independent per dimension, and the denoising step of diffusion has this phi t as the variance to add element of stochasticity and reduce the harmony between the range space and null space. So we include this gamma t into the equation, so the sum of these two variances is almost equal to what it used to be in before when we had this element of stochasticity added. And the final question is, how about the lambda t? For cases that the element of noise in observation is not much and the multiplication of the standard deviation times at is less than the standard deviation of a diffusion model in its time step t, we keep it as 1. And that means to correct the range space as much as we can. But for the cases that the noise in observation is a lot, we define it using this fraction that if you substitute it in the formula, you can see that it removes at and sigma y, and all it remains is sigma t on the left side and also on the right side. So this gamma t has no option to be 0. And that means the element of noise in observation is so much that we don't want a diffusion denoiser to add any element of a stochasticity as a noise, because we already have a lot of noise and we want to denoise all of it. And yeah, that's all we need to know about this DDNM plus work. If you think it's complicated, I have to tell you a bad news. That remember in the beginning, we assumed that the noise comes from the distribution, that all the dimensions are independent. Well, what if they are not? So the authors go one step further and have a more generalized assumption that makes it even more complicated. I'm not going to go into that detail because it is already too complicated, I believe. But in case we have this assumption of dependence, then we can define sigma t and phi t using this equation that is similar to what we had before, except that we have a unique lambda and gamma per dimension. And in addition, we have a V matrix that is coming from SVD decomposition of the degradation matrix. If you are interested, you can read it in the supplementary material yourself to understand the math behind it. But let's move on to the part I said this sigma y is unknown and it's a hyperparameter, and let's see how we can choose it. In practice, when we have an observation y like this and we want to do painting and colorization and probably a bit of super resolution, you can see that the choice of sigma y as hyperparameter matters. When it is 0, we still achieve a reasonable result, but once you zoom in, you can notice that there are some noises in the pixels. And as you increase the sigma y hyperparameter, you can see that it becomes more smooth, but at the cost of getting blurry if you do it much. And the final challenge I want to mention about this paper is that for the case that we have an extremely challenging cases, like cases you want to do 32 times super resolution or 60 times super resolution, while it also receives a high degree of noise. In these challenging cases, even when you do DDNM plus, you see these results that doesn't seem good enough. But to tackle these issues, authors have proposed a simple solution that is time travel. And in solution, they say once we are at xt and we want to go to xt minus L, instead of going it as usual, let's come back to xt plus L and do it sometimes and then go from xt plus L to xt minus L. And this way, once we go to xt plus L, we're at a position that is more noisier, and the denoiser has more option to refine the null space. And this way, we can give the model a chance to fix whatever it is missed in the past to have a better future. And as easy as that, you can fix it and get a more realistic result. And yeah, that was all I wanted you to know about the DDNM method. I agree that was a tough one, but I hope both of us are on the same page. If you enjoyed it, don't forget to like and subscribe, and until the next video, goodbye.